Welcome back to the deep dive. Today we are tackling something, well, pretty revolutionary, I think.
Absolutely. We're looking at this convergence, this meeting point of large language models, KGS knowledge graphs, and good old search engines.
Right. And we know you, our listeners, you come here for that deep insight. You want to get up to speed fast on complex stuff. And honestly, it doesn't get much more complex or faster moving than this area right now.
It really doesn't. The material we've gathered, it paints a really clear picture. You've got these three individually quite powerful technologies.
Yeah. Powerful but flawed in their own ways.
Exactly. And now they're kind of learning to work together. The goal, to shore up each other's weaknesses. You know, LLMs are amazing with language, but sometimes they just make things up.
The hallucination problem, yeah.
Precisely.
Mm.
And knowledge graphs, they're packed with facts, super structured, but accessing them, that's tricky for the average person.
And search engines, well, they're trying to move beyond just matching keywords, aren't they?
They have to. So our mission today, really, is to unpack how they're merging. We'll be looking closely at things like RAG, that's retrieval augmented generation.
Right, this key architecture.
Yeah, it's designed to create systems that are, more factually sound, systems that can pull in real-time information.
And this fundamentally changes the game for things like semantic SEO, how content gets found.
It absolutely does. So we'll start by outlining those challenges, the limits of each technology on its own, and then we'll dive deep into how they fuse together.
Okay, let's get into it. Let's unpack this collaboration.
Right, so first pillar, the one everyone's talking about, large language models, LLMs.
Yeah, the GPTs, the BERTs, all those big names.
Exactly. These are, at their core, really sophisticated AI systems. Their whole thing is processing, understanding, and crucially generating text that sounds like a human wrote it.
And they do that using these massive, deep neural networks. The large language model isn't kidding, right? The scale is just immense.
It really is.
Yeah.
Think about something like GPT-3. We're talking, 175 billion parameters?
Yeah.
That's the scale we're dealing with. They're trained on just colossal amounts of text data from the internet, books, you name it.
And that sheer size lets them learn the patterns, the statistics of language incredibly well.
That's the key. And the foundation for pretty much all modern LLMs, as our sources point out, is this thing called the transformer architecture.
Ah, yes. The paper attention is all you need. Revolutionize the field.
It absolutely did. It lets the models handle long sentences, understand context across big chunks of text much better than older methods. And based on how these transformers were put together, we generally see three main types of LLMs.
Which people often mix up, especially if they only use the end product, like a chatbot.
Very true. So first up, you've got your decoder-only models. Think of the core GPT series here. Their main job is predicting the very next word or token based only on the words that came before.
That's what makes them so good at generating that smooth, coherent text, right? Like writing an email or a story.
Exactly. Then second, you have encoder-only models. BERT is the classic example. These guys are all about deep understanding of the context.
Okay, hold on. The sources mention something specific for BERT. Masked language modeling. Why does an encoder-only model need that? What's it doing?
Good question. That's a really key training technique for models like BERT. During training, some words in a sentence are deliberately hidden or masked. The model's job is to predict those specific hidden words.
So it's like filling in the blanks.
Sort of, but crucially, it has to use the context from both sides, the words before the blank and the words after. This forces it to develop a much deeper bidirectional understanding of the sentence structure and meaning.
Which makes it better for tasks that need that deep understanding, like figuring out sentiment or classifying text.
Precisely. It's less about generating new text and more about analyzing existing text. And finally, the third type, encoder-decoder models. BART is a common one. These combine both functions. They have an encoder to understand the input and a decoder to generate the output.
Useful for things like translation or summarizing a long document.
Exactly. Summarization, translation, question answering, where you need both understanding and generation. So you have these incredibly powerful architectures, but, and this is a big but, they all have some pretty deep inherent flaws.
Flaws that stop them from being, perfectly reliable sources of truth on their own.
Right. The first big one is often called the black box problem, and a major part of that is knowledge getting stale.
Knowledge obsolescence.
Yeah. These models, they're like snapshots in time. They only know what they were trained on up to the point their training data was collected. If a model was trained last year, it knows nothing about this morning's news.
So its knowledge is frozen.
Frozen's a good word for it.
Yeah.
And the only way to update it traditionally is this massive, incredibly expensive retraining process. You
Yeah.
have to feed it all the new data and basically rebuild it. Computationally, financially, it's a huge barrier.
Okay, so that's the freshness problem. But even the stuff they did learn during training, it's not always right, is it? That's the hallucination issue.
That's the other major headache. LLMs aren't like databases searching for facts. They're prediction engines. They predict the next most statistically likely word based on the patterns they learned.
So if a fact wasn't super common or was maybe ambiguous in the training data?
The model might just generate something that sounds plausible, fits the pattern, but is completely wrong. It hallucinates an answer. How accurate a factual statement is often depends heavily on how often that fact popped up in its training data. Rare facts. Forget about it. High risk of error.
Okay, so stale knowledge, potential for making stuff up.
Yeah.
What else?
The third challenge is about structure, or rather, the lack of it in their output sometimes. We call it the unstructured generation problem.
Meaning they're great at writing paragraphs, but not so good at, say, outputting data in a specific format?
Exactly. You can ask one to generate a story, and it's amazing.
Yeah.
But ask it to output, say, a complex nested list following very specific rules or data formatted perfectly for a spreadsheet. It often struggles. It might ignore the overall structural requirements.
Why is that?
Because during that massive pre-training phase, they learn mostly from local context the words immediately around each other. They don't always internalize the kind of global, syntactic, or formal structural knowledge needed for things like logical deduction or precise structured data output. They're masters of prose, not necessarily masters of formal structure.
Okay, so LLMs are fluid, powerful, but potentially inaccurate and unstructured. That feels like a perfect setup for the next pillar, knowledge graphs.
It really is. Knowledge graphs, or KGs, are almost the polar opposite in some ways. They represent information as a highly structured summary. They're all about the precise connections, the correlations between concepts.
So where the LLM is like a vast flowing river of text, the KG is more like a meticulously organized library or map.
That's a great analogy. Think of a KG as a network. You have nodes or vertices which represent entities, things like people, places, companies, concepts, usually nouns from natural language.
Like Paris, Eiffel Tower, France.
Exactly. And then you have the connections between them, the edges. These edges define the semantic relationships. So you'd have an edge from Eiffel Tower to Paris, labeled as located in, and an edge from Paris to France, also labeled as located in.
It explicitly maps out how things are related.
Precisely. And crucially, this isn't just some ad hoc structure. KGs are typically built on standards from the Semantic Web Initiative.
Things like RDF and LLM.
Yes, RDF Resource Description Framework and LLM Web Ontology Language. These are formal standards for defining entities and their relationships. They ensure consistency and allow machines to process the information unambiguously.
And this structure allows for very specific ways of querying the data, right? You mentioned Sparkle.
Right. Sparkle is essentially the query language for these structured knowledge bases, much like SQL is for relational databases. It lets you ask really complex structured questions like, find all cities in France with a population over 1 million that have a landmark designed by Gustave Eiffel.
Wow, okay. You couldn't easily ask an LLM that and be sure of the answer.
Not with the same level of certainty or structure. So, KGs give you factuality, clear sources, because the relationships are defined, and they're relatively easy to update. You just add or modify nodes and edges. No need for that massive retraining like with LLMs.
Okay, so KGs sound amazing. Factual, structured, updatable. Why haven't they just taken over everything already? What's the catch?
The big hurdle is the access challenge. All that beautiful structured knowledge is kind of locked away from the everyday user.
Because you need to know Sparkle or understand the underlying structure, the ontology.
Exactly. Your average person searching the web doesn't know Sparkle. They don't know the specific names of the entities or relationships defined in the graph's ontology, its conceptual map. They just want to type a question in plain English.
So the structure that makes KGs powerful also makes them hard for most people to use directly.
Precisely. There's a mismatch between the user's natural language query and the graph's formal structured language. That's the gap we need to bridge.
Which brings us nicely to the third pillar, the familiar search engine. Google, Bing, DuckDuckGo, our main window onto the web for decades.
Right, and they've been incredibly successful at what they were designed for in the Web 2.0 era, finding relevant documents based on keywords.
But things are changing, aren't they? We're moving towards what people call Web 3.0, the semantic web, where data itself has meaning. And the old algorithms are starting to feel a bit strain.
They are. User expectations have shifted. We don't just want a list of 10 blue links anymore. Increasingly, we want direct answers, specific facts extracted from that growing sea of semantic data.
We want the search engine to understand the meaning of our query, not just the words.
Exactly. And this leads to what our sources call the user intent gap. It's especially noticeable with these things called long-tail queries.
Long tail, meaning very specific, less common searches.
Precisely. Think of a query like, what's the average lifespan of a specific breed of parrot kept indoors? It's a simple factual question, but it's narrow.
Right, not something millions of people are searching for every day.
So very few high-ranking websites will have a single, explicit sentence answering that exact question. Traditional search engines, trained on broader patterns, struggle. They might give you general articles about parrots or pet care.
When all I wanted was that one specific number or fact.
Exactly. They lack the fine-grained understanding and the ability to synthesize information from multiple sources to answer that very specific niche question effectively.
So you have LLMs that can generate answers but might be wrong, KGs that have the facts but are hard to query, and search engines that are great at finding documents but struggle with specific factual questions.
You've nailed it. And that tension, that set of complementary weaknesses and strengths, is exactly why we need to bring them together. The goal is that perfect answer delivered in natural language, grounded in facts.
Okay, so the stage is set. LLMs are fluent but flawed. KGs are factual but inaccessible. Search is evolving. The obvious next step seems to be making them work together. This brings us to KGLMs, knowledge graph enhanced LLMs.
That's the core idea. It's about leveraging the strengths of one to compensate for the weaknesses of the other. The KG provides the factual grounding, the structure, the consistency that LLMs lack.
And the LLM provides the natural language interface, the ability to understand a user's plain English question and translate it into something the KG can work with, or use the KG's output to form a natural answer.
Exactly. It's a symbiotic relationship. And what's really interesting is that this integration, this enhancement, isn't just a single switch you flip. Our sources show it can happen at different points in the LLM's life cycle.
Right, it's a strategy, not just one technique.
Yeah, the research breaks it down into roughly 3 main approaches for injecting that structured knowledge from the KG into the LLM.
Okay, let's walk through those. When can you add the KG smarts?
So the earliest point is before training. The idea here is to improve the quality of the data the LLM learns from in the first place.
How do you do that? Mix KG facts into the training text.
Pretty much. You construct what's called KG extended text. You basically take facts and relationships from the knowledge graph, like Paris is capital of France, and you weave them directly into the raw text documents that the LLM will be trained on.
So the model sees these explicit factual connections right from the start, alongside the regular sentences.
Exactly. It gives the LLM a richer, more factually grounded input diet during its initial massive learning phase.
Okay, that makes sense. What's the next stage?
The next opportunity is during training. This is more complex because you're actively trying to get the model to learn from both unstructured text and structured graph data simultaneously.
Yeah, that sounds tricky, like teaching it 2 different languages at once. How does that work?
It involves sophisticated techniques. Sometimes researchers use specialized neural networks called graph neural networks, or GNNs. These are designed specifically to process the structure of graphs.
So you have one part of the model reading text, another reading the graph.
Kind of. Or you use advanced attention mechanisms, ways for the model to focus on relevant information, to fuse the knowledge from both sources. Models like ERNIE, mentioned in some sources, do this. They might combine the standard word representations with representations of the entities from the KG.
So the model learns, for instance, that the word apple in the text is strongly linked to the specific Apple Inc. entity in the KG, not just the fruit.
Precisely. It builds these knowledge-enhanced representations directly into the model's core during training. It's about deep fusion.
Okay, so before training, during training, what's the third way?
The third approach is post-training fine-tuning. This happens after the main LLM has been trained. You take that general purpose model and you fine-tune it further, either using knowledge-extended data or specifically on tasks that require reasoning over the KG.
This sounds like where you'd specialize a model for a specific domain, like medicine or finance.
Exactly. A really powerful technique here involves using knowledge prompts.
Knowledge prompts. How does that differ from a regular prompt?
Instead of just asking the LLM a question directly, you first go to the knowledge graph, retrieve relevant facts and relationships related to the question, format those facts into a structured piece of text, the knowledge prompt, and then you feed that prompt along with the original question into the LLM.
Ah, so you're explicitly giving the LM the relevant facts it needs, right there in the context window, before it generates the answer.
You got it. It directly guides the LLM's reasoning, grounds it in the specific factual knowledge from the KG, makes it much more likely to give an accurate, relevant answer, and reduces that chance of hallucination. It's a very effective way to inject structure just when it's needed. Hashtag 2.2 domain-specific application examples.
This combination, the synergy between LLMs and KGs, it's not just theoretical, is it? It's showing real value in fields where just being plausible isn't good enough. Accuracy is paramount.
Absolutely. Healthcare is a prime example. Look at the development of models like MetaLM or its predecessor, MedPolM. These aren't just generic LLMs. They are foundation models specifically fine-tuned for the medical domain.
And that fine-tuning involves leveraging medical knowledge graphs, doesn't it?
Yeah.
Standardized terminology, drug interactions, disease relationships.
Precisely. The KG provides that structured, authoritative medical knowledge. And the results. They can be pretty stunning. MedPolM2, for instance, hit an 86.5% accuracy score on questions styled after the U.S. medical licensing exam.
Wow. And the sources said that was a huge jump, like 19% better than the previous version.
A massive leap. And a significant part of that improvement comes from that structured grounding. Medical language is complex, full of synonyms, prone to ambiguity. The KG helps enforce consistency, aligns the model with standard terminologies, and reduces the risk of it generating plausible but incorrect medical information.
But it's not just about the tech, is it? The sources really emphasize the human element, especially in high-stakes areas like medicine.
Critically important. The success of something like MedPolM isn't just about building a bigger model or feeding it more data. It relies heavily on really thoughtful evaluation strategies. You need to test it on clinically relevant tasks.
And you need doctors involved.
Absolutely. Deep partnership with clinicians, with ethicists, with cross-functional teams is essential. You need that human expertise to guide the fine-tuning, validate the outputs, ensure safety, and build trust. It's very much a human-in-the-loop system.
We see a similar pattern in cybersecurity, too, with platforms like SecLM. Security is another area where authoritative data is key.
Right. SecLM aims to help security professionals deal with a huge volume of alerts and data they face. It combines LLMs with authoritative security data, which you can think of as a specialized security knowledge graph or database, plus a flexible planning framework.
So it helps analysts make sense of complex, often deliberately obscured security events.
Exactly. The sources give a great example. Analyzing an obfuscated PowerShell command. Attackers often encode commands using things like base64 to hide what they're doing.
Making it hard for a human analyst to quickly see the threat.
Right, they'd have to manually decode it, figure out what each step does. SecLM can automate much of this. It uses tools to decode the command, then leverages its security knowledge base, its KG, which contains information about known malicious IP addresses, typical attack patterns, safe file locations, etc.
And it doesn't just decode it, it explains what it means.
Yes, it provides a clear, natural language explanation. In the example, it identifies that the script connects to a remote computer, downloads a file to a sensitive location, and then disconnects.
And crucially, it flags it as malicious.
Precisely. It explains why it's malicious, because the actions match a pattern of unauthorized remote access, likely aimed at stealing data. The KG provides that authoritative context to make the judgment call. It turns cryptic code into actionable intelligence, saving the analyst huge amounts of time.
Okay, so we got this smarter, more factual AI brain emerging from the LLM-KG partnership. But how does this actually change the experience for someone using a search engine? How do these smarts get delivered? This feels like the core of the LLM-4 search idea.
It really is. LLMs and the knowledge they can access from KGs or elsewhere are starting to enhance the entire search process, from the moment you type your query to the final list of results you see.
Affecting multiple stages.
Yes. Broadly speaking, 3 key stages: how your query is understood, how the web content is indexed and understood by the engine, and how the results are ranked. Hashtag 3.1 LLM for query augmentation.
Let's start at the beginning with the user's query. How are LLMs helping there?
They're acting like really smart interpreters of user intent. Even before the search engine looks for documents, the LLM can help refine what the user is really asking for.
Going beyond just the keywords entered.
Exactly. One way is through query recommendation. By analyzing vast amounts of search data and anonymized query logs, user behavior patterns, LLMs get very good at predicting what you might be trying to find.
So they suggest related searches or rephrase your query to be more effective.
Yes. suggesting relevant keywords, maybe alternative phrasings that better match how information is actually structured online, or even reflecting current trends related to your topic. It helps you formulate a better search from the get-go.
And they also help with our inevitable typos and grammar mistakes.
Mercifully, yes. That falls under query correction or improvement. Because LLMs have such a deep understanding of language structure, they're great at recognizing common spelling errors, grammatical mistakes, or just awkwardly phrased queries.
So they can suggest the correction, did you mean?
Right, ensuring the search engine actually searches for what you intended to ask, not the garbled version you typed. It makes the whole experience smoother and less frustrating. Hashtag 3.2, enhanced indexing and information extraction.
Okay, so the query is clearer. What about the other side, understanding the billions of pages on the web? How do LLMs change indexing?
This is a huge area. Traditionally, indexing was heavily based on keywords found in a document. LLMs allow for much deeper semantic understanding of the content.
Moving beyond just listing words to understanding concepts and relationships within the text.
Precisely. LLMs can be used for tasks like high-quality content summarization, automatically extracting the key topics and arguments of a page. This helps the search engine build a much richer, more accurate index. It knows what the page is about, not just what words it contains.
And this seems like the perfect place to connect the web content back to the structured world of the knowledge graph, right? Through entity linking.
Absolutely critical.
Yeah.
Entity linking, sometimes called semantic annotation, is the process of identifying mentions of real-world entities, people, places, organizations, concepts within the text, and linking them unambiguously to their corresponding entries in a knowledge graph.
So when a page mentions Apple, the system figures out if it's talking about Apple the company, Apple the fruit, or maybe Apple Martin the person, and links it to the correct KG entry.
Exactly that. It disambiguates. And this is often done using powerful pre-trained language models, like BERT, which are good at understanding context. They encode the mention of the entity and the surrounding text to make the right link.
But the sources mention a challenge here, word embeddings and entity embeddings living in different spaces. What's alignment embedding about?
Ah, yes. Think of it like this. The LLM represents words as mathematical vectors in one space, and the KG might represent entities as vectors in a slightly different space. For them to work together seamlessly, you need to align these spaces.
Like creating a common coordinate system.
That's a good way to put it. Alignment embedding techniques aim to map both the word vectors and the entity vectors into the same vector space. This allows the system to accurately measure the similarity or relatedness between a word mentioned in the text and an entity defined in the graph. It ensures Apple, the word, and Apple Inc. The entity are recognized as being conceptually close.
Makes sense. You need a common language. And what about topical coherence?
This is about using context dynamically. Once the system successfully links one entity in a document, say, it identifies Tim Cook and links him to the CEO of Apple Inc., it uses that information to help with the next entity it encounters.
So if the next sentence mentions the CEO, the system has a stronger clue it refers to Tim Cook because of the previous link.
Exactly. It accumulates knowledge as it processes the document. This topical coherence helps resolve ambiguity for entities that might be harder to link on their own, leading to a more accurate and consistent semantic understanding of the entire page. Hashtag 3.3 LLMs in ranking algorithms. Learning to rank. Okay, so we have a better query, and the engine has a deeper understanding of the pages. Now comes the crucial step, ranking. Out of potentially thousands of relevant pages, which ones show up at the top? This is where learning to rank, or LTR, models come in.
Yes, LTR models are machine learning models specifically trained to predict the optimal ordering of search results. But training them requires vast amounts of high-quality data, basically, examples of queries and judgments about how relevant specific web pages are to those queries. And getting those relevance judgments accurately and consistently, especially at scale, must be a huge challenge.
It's a major bottleneck. This is where LLMs can make a massive contribution. Given their deep language understanding and ability to reason about relevance, they can be used to automatically generate these crucial relevance annotations for training the LTR models.
So instead of relying solely on human raters or click data, you can use an LLM to assess relevance.
Exactly. It can significantly scale up and potentially improve the quality of the training data. And LLMs can do this in a few different ways, corresponding to different LTR approaches.
Okay, what are those approaches?
The first is point-wise LTR annotation. Here, the LLM looks at a single query document pair and assigns an absolute relevance score like perfect, good, fair, bad. It's judging each document independently.
Simple enough. What's next?
Second is pairwise LTR annotation. This focuses on relative judgments. The LRM is given a query and two documents, A and B, and has to decide which one is more relevant. Is A better than B, or is B better than A?
Ah, so it's learning the relative order, which is really what search ranking is all about.
Precisely. Many believe pairwise is more directly aligned with the ranking task. And the third, most complex approach is listwise LTR annotation.
Assessing the whole list at once.
Yes, the LLM evaluates the quality of an entire ranked list of documents for a given query. It considers not just individual relevance, but also factors like diversity and overall coherence of the result set.
Wow. So LLMs can provide these nuanced relevance judgments at different levels of granularity, which then feeds into training better, smarter ranking algorithms.
Exactly. By leveraging LLMs for annotation, search engines can build more effective LTR models, ultimately leading to search results that better match user intent and information needs.
Okay, we've seen how LLMs and KGs enhance each other and how they're upgrading search behind the scenes, but how does this all come together in a practical system that actually delivers those improved factual answers? This seems to be where retrieval augmented generation, our array, really enters the picture.
RGAE is absolutely key. You can think of it as the architectural pattern that makes this LLM-KG search synergy operational. It was specifically developed to address those core LLM limitations we talked about earlier.
The staleness, the tendency to hallucinate, the difficulty with questions outside its training data.
Exactly. RGAE is designed to combat those by dynamically bringing external knowledge into the LLM's process right when it's needed. It stops the LLM from having to rely solely on its own, potentially outdated or flawed internal memory.
So how does it actually work? If I type a question into a system using RGAE, what happens under the hood?
Okay, so at the moment you submit your query, this is called inference time. The RGAE system first performs a retrieval step. It takes your query and searches an external knowledge source.
What kind of source? A search engine? A database?
It could be various things. Often it's a search engine index, either the public web or a company's internal documents. Or, crucially, it could be a structured database or a knowledge graph, especially for those domain-specific applications. The system retrieves a set of documents or data snippets deemed relevant to your query.
Okay, so it finds some potentially relevant info. Then what?
Then comes the augmentation part. The content from those retrieved documents or data snippets is extracted and then injected directly into the prompt that's fed to the LLM, alongside your original query.
Ah, so it's like giving the LLM a cheat sheet or briefing notes relevant to my specific question right before asking it to answer.
That's a perfect analogy. The LLM isn't asked to answer from memory alone. It's asked to answer based on the provided context. This retrieved information grounds the LLM's response in external, often more up-to-date and factual information.
Which forces it to stick closer to the facts in those notes rather than just predicting the next likely word sequence from its training.
Precisely. And this is where it becomes incredibly valuable for you, the learner, needing reliable information quickly. The benefits of RHEG line up perfectly with those needs. Hashtag TAC 4.2 benefits of ARG for the learner.
Okay, let's break down those benefits. What does RG deliver specifically for someone trying to get smart on a topic?
Well, first and foremost, freshness in real-time data. Because the retrieval happens at the time of the query, RShe systems can pull in the latest information from their source, whether that's the live web via a search engine or recently updated internal documents.
So unlike a standard LLM, I can ask a RAG system about something that happened just hours ago, and it can potentially find and incorporate that information.
Exactly. It overcomes that knowledge cutoff problem inherent in static LLM training. Second, RGAE significantly improves responses for those tricky long-tail queries.
The very specific niche questions.
Yes. Where a standard search engine might struggle to find one perfect page, REC can retrieve relevant snippets from multiple documents, even if each snippet only contains part of the answer. The LLM can then synthesize these pieces into a single, coherent, and precise answer.
So it's better at piecing together information for specific, narrow, factual needs. What about trust?
That's the third major benefit: provenance and fact awareness. Because the LLM's response is generated based on specific retrieved documents, the system can often cite its sources.
Ah, so it can show you where it got the information from.
Potentially, yes. This traceability dramatically increases trustworthiness. You're not just getting an answer from black box. You can, in theory, check the original sources. This is huge for research or any situation where verification matters.
Definitely. Anything else?
Finally, our REG systems tend to produce better coherence and summary generation. Because the LLM sees the context from multiple retrieved documents, it gets a broader understanding of the topic. This allows it to generate summaries or explanations that are not only factual but also well-structured and capture the key points effectively. It's great for digesting complex information quickly, #tag 4.3 RIG, and knowledge graphs.
Now, you mentioned the retrieval source could be a search engine index, but it could also be a knowledge graph. How does using a KG as the retrieval source for RAG change things?
Using a KG adds another layer of reliability and structure. When R retrieves information from a KG, it's not just getting snippets of text, it's getting structured facts, entities, and relationships that have already been verified and organized.
So the notes you're handing the LLM are even more precise and trustworthy.
Exactly. For domain-specific applications, medicine, finance, internal company knowledge, retrieving from a well-maintained KG provides superior consistency, allows for more complex reasoning because the relationships are explicit, and improves the interpretability of why the system gives a certain answer. You're feeding the LLM high-quality structured knowledge.
But querying a KG, especially a large one, needs to be fast for ERGI to work in real time, right? You can't wait minutes for a database query.
Absolutely. Speed is critical. The retrieval step has to be almost instantaneous. This is an active area of research. The sources mentioned work on optimized search methods specifically for KGs.
Like that central graph model idea?
Yes, concepts like that. The goal is to develop parallel search techniques that can quickly query large KBs and return not just individual facts, but compact, relevant subgraphs, answer graphs that contain the rich, structured information needed.
So fast, structured retrieval feeding directly into the LLM via REG, that sounds like a powerful combination.
It really represents the state-of-the-art in many ways, combining the speed and breadth of search, the structure and factuality of KGs, and the natural language fluency of LLMs.
Okay, this technological fusion, LLMs, KGs, search, RAG, it's fascinating from a technical standpoint.
Yeah.
But let's bring it back to the practical world. How does all this change things for businesses, for content creators, for anyone trying to get their information seen online? This has to connect to SEO, right?
It connects directly, but it forces a shift in thinking. We're moving towards what's increasingly called semantic SEO. The old rules of just stuffing keywords onto a page are becoming less and less effective.
Why the shift? Is it because people are searching differently?
Partly, yes, but it's also because the endpoints are changing. Think about the rise of smart speakers, Alexa, Google Home, and all sorts of conversational AI bots and assistants. People are asking questions, not just typing keywords.
And those devices need to understand the meaning to give a good answer. They can't just read out a web page.
Exactly. For your information to be surfaced through these channels, you need to be, as some sources put it, highly hearable and visible. Your content needs to be structured in a way that these AI agents can understand semantically. Hashtags, tags, tagged, 5-cut-1 knowledge graphs, and website visibility.
So how do you make your content understandable to an AI?
The key is semantic annotation. This means marking up your website content with machine processable descriptions. You're essentially adding labels that explain what the different pieces of content are and how they relate to each other.
Using standardized formats.
Yes, crucially, using shared vocabularies. The most important one here is schema.org. It's a vocabulary that was collaboratively launched by the major search engines, Google, Bing, Yahoo, Yandex, specifically for this purpose.
So you use schema.org markup to tag things on your page like this is a product, this is its price, this is an event, this is its date and location.
Precisely. You're adding a structured data layer on top of your human-readable content. This markup is the language that search engine bots, knowledge graphs, and AI assistants use to truly understand your content, to extract the entities and relationships accurately.
And this directly feeds into things like the Google Knowledge Graph.
Absolutely. The Google Knowledge Graph aims to be this massive repository of structured information about the world, drawing heavily from semantically annotated data it finds on the web. If you mark up your site clearly using schema.org, you're essentially helping Google and other engines understand your information and potentially incorporate it into their own KGs.
Which means your facts, your entities, might be the ones Google uses to directly answer a user's query, perhaps in one of those featured snippets or voice search answers.
That's the goal. Businesses are increasingly aware that SEO, specifically semantic SEO, is their primary tool for engaging with and influencing these powerful knowledge graphs, ensuring their information is represented accurately and authoritatively.
Okay, so if the goal is to influence the knowledge graph through semantic SEO, what are the actual tactics? How does a business do this?
It builds on traditional SEO but adds a focus on structured data and entity management. Foundational things like strategic keyword selection are still important. You need to understand the language users use to ask questions about your entities.
But it goes beyond just keywords on the page.
Yes, a huge part of it is actively managing your presence in authoritative directories and platforms that feed directly into the knowledge graphs.
Like Google My Business for local businesses.
Exactly. Keeping your GMB profile completely up-to-date, accurate hours, services, address, photos, and actively managing it by posting updates, responding to reviews, answering questions. This is direct structured data injection into Google's ecosystem.
Because GMB is essentially a structured database that Google trusts implicitly for local information.
Precisely. Every update, every answered review reinforces the relevance, accuracy, and authority of your business entity in the graph. Consistency across all platforms where your business is listed is also key.
So it's less about trying to trick an algorithm with keywords and more about providing clear, consistent, structured information about your core entities.
That's the fundamental shift. The ultimate aim of semantic SEO is to optimize for those conversational interfaces, for the direct question-answering capabilities that are built on top of knowledge graphs.
How does that work?
By providing rich entity information and clear relationships via schema.org and platform management, you make it easier for the AI systems. Some advanced approaches even use KGs to automatically generate training data for the natural language understanding (NLU) models that power these conversational agents. It all comes back to enabling accurate question answering over the knowledge graph.
So you're optimizing for the facts to be easily found and understood by machines, not just for the document to rank highly for humans.
You got it. That's the essence of semantic SEO in this new landscape. Optimize the facts, the entities, the relationships, so the machines that increasingly mediate our access to information can understand and use them accurately.
Wow, that really ties it all together. We've gone from these separate, powerful, but limited technologies
To this incredibly integrated system where they're all working together. #tag outro.
It's been quite a journey today. We started with the individual pillars, the fluent but sometimes flaky LLMs, the factual but hard to access KGs, the evolving search engines.
And we saw how they're coming together, really, through architectures like R acting as the glue. Our ad leverages search for speed and freshness, and increasingly KGs for structure and reliability to make LLMs truly useful, factual, current, and domain-aware.
Fundamentally changing search, and as we just discussed, forcing a rethink of SEO towards semantics.
And that synergy is just so clear, isn't it? LLMs crack the code for natural language access to KGs. You can finally just ask a graph a question.
Right, solving the KG's access problem.
And in return, the KG provides the grounding, the structure, the reasoning ability, the interpretability that vanilla LLMs desperately need. It addresses the LLM's factuality and consistency problems. They really do cover each other's weaknesses perfectly.
It's a powerful combination. But thinking back to those high-stakes examples, like MedPalm in healthcare.
Yeah, the success there wasn't just tech.
No, the sources stressed it was heavily dependent on really careful evaluation, on focusing on real clinical value, and critically, on that deep partnership with the the clinicians. They were essential for validation, for alignment.
Which leaves us with a final thought, perhaps, for you, the listener, to mull over as this technology continues its rapid advance.
Okay, let's hear it.
If these next-generation AI systems, the ones that are networked, pulling real-time data, grounded in knowledge graphs, achieving high accuracy, if their success and trustworthiness depend so fundamentally on intensive human oversight, on validation by domain experts,
Then maybe the biggest challenge ahead isn't just scaling the AI models themselves, adding more parameters, more data.
maybe not.
Yeah.
Perhaps the real bottleneck, the truly hard scaling problem for this next era of AI, isn't the parameters, but scaling the trust. Scaling the human expertise that's required to constantly validate, align, and ensure these incredibly powerful systems are actually working correctly and beneficially in the complexities of the real world.
Scaling human expertise and trust, that's a profound challenge indeed, something to definitely think about.
Indeed. Until our next deep dive.
Thanks for joining us on the deep dive. We'll talk to you next time.